times the square root of, now I never did this, but let's do it, we can do it just visually. What's partial of g with respect to y? 0 squared, plus partial of g with respect to z, negative 1 squared, plus 1 dA, right? dA. That's just root 2. So I have this integral now. Double integral over d of 1 minus z, root 2, let's put the root 2 in front. Root 2 comes out of the double integral, 1 minus z dA. Yes?
I don't get why it's just 1 minus z and there's the z value. Can you just like use the x component?
Because you're living on this blue, right? Because you're living on this blue, the x coordinate is always 1 minus the z, right? So when I go and replace that x right there, I have to replace it with what it is, right? And I'm saying that x is a function of y and z. That's the only reason I can use this shortcut is because I'm saying x is a function of y and z. So everywhere I see an x, I've got to replace it with whatever that function is. That's what this means. Wherever I see, whatever this function is up there, wherever I see x's, I replace it with that function. Any y's, I just leave them as y's. Any z's, I leave them as z's. So that's why that x up there gets replaced with this, and then this is the rest of it.
Oh, so there's like no z's in the equation, so it just be big.
There's no y's?
Y is root.
You said no z's. There's no z's in the equation? You're lost? Yes.
Is it like if the function was like x, y, z, then you would have 1 minus z times y times z?
Yeah, if that function up here was x times y times z, you would have this times y times z. And then you would have the square root, and that would be the same.
So you're plugging it into the original.
That's right. This right here means to look at that scalar function. See, unfortunately, our scalar function is boring here, right? It's just x. So the only thing I have to worry about is what's x? Well, x is this. But if there were y's or z's, I would have to plug those in as well. Yes?
So that function at the top is in terms of x. If that wasn't solved for x and it was like y equals something, then we would have to solve for x in order to plug it back in.
Where? If what wasn't solved for x? Wait, what?
Another shape of the
Oh, yeah. Well, if it was solved for something, like let's say it was z minus, let's say it was z equals 1 minus x, like solved the other way, then we would have to solve for x.
It didn't have any x.
Then it would not look like that. It couldn't look like
So
that.
it's
Then,
like this special.
yeah, this surface is going to dictate what the equation looks like, right? It would be impossible to have something that looks like this without having x and z in it and no y's, right? All right, can I continue? We're not done, right? Because I need to do this double integral now. Where's the domain of this? Because we're looking at D, right? S is the surface. Where's its domain? It lives in the what z plane? YZ plane. And what does it look like in the YZ plane? Circle, right? Disk, really, right? It's a disk. So if we project this blue onto the YZ plane, it's kind of hard to see, but the projection of that would be that, right? And that lives in the YZ plane. So I need to actually look at that projection. So D, right, for this is going to look like in the YZ plane a disk, right, with what radius? 1. How do you know it's 1? Why? Because you can see it here? Well, doesn't it live on that green cylinder? And the green cylinder has the equation y squared plus z squared equals 1, which dictates what the radius is, right? So you know that this is 1. I'm doing a double integral over that region, which is a polar region. So now I've got to go to polar, right? I'm going to go to polar now. So I'm going to go theta's between 0 and 2 pi. And then my radius is going to be between 0 and 1. And now I make a polar conversion. But we have to be careful here. We have to be extremely careful because we are doing YZ, right? Not XY. So since we're doing YZ, we're making the switch that the Y is the R cosine theta, and the Z is the R sine theta. Do you see the slight difference there? Because we're in the YZ plane, not the XZ plane. I'm trying to remember what it was like to be a Cal 3 student. It's hard to remember that long ago. It's just, I don't know. Does it feel like just like a lot of information, or feels like a lot?
It's all like
Root 2. All right, domain. I can put limits of integration. Let's go 0 to 2 pi, 0 to 1. All right, 1 minus z becomes 1 minus r sine theta, right? 1 minus r sine theta. And then r, because we did polar, right? R, and then dr d theta. And at that point, we are in business, right? I'm going to go and do this on the computer because I don't feel like doing it, right? But we could do that, right? Double integral. We're going to go 0 to 2 pi, 0 to 1.
Do we get computers on this?
Yes, you get computers. No. I won't. I wouldn't ask you to go all the way. Sine t times r dr dt. I believe this comes out to be pi. Yeah, comes out to be pi. All right, turns out to be pi. All right, without going through the work. Can you all take that on faith? Answer's pi. Okay, so this is pi. Now, look, Wolfram alpha can't do that, right? Wolfram alpha can't do the problem for you. It can do the integral for you, but it can't do the setup. Yes?
Well, because where's the square root of 2?
Oh, root 2. Sorry. Yeah, I forgot to put the root 2 in. Thank you. Thank you. Yeah, it's here, but I forgot to put it there. Are we done? 2 surfaces down, 1 to go. So the first one gave us 0. The second one gives us root 2 pi, thank you. And let's see what the last surface gets us. Let me erase things. We're talking about S3 now, right? Just as a little informal poll here, are you glad that we took time to talk about the parameterization of these, or you feel a little more comfortable looking at these and Okay. Hey, wait a minute. Can we look at the y squared plus z squared equals 1? Can we look at that as a function of can we look at it as a surface, like where the z is a function of x and y, or the y is a function of x and z? No, right? It wraps around. You can't do it. All right? We have no option on this green one but to do it with the crude method we learned last class. Okay? Sorry.
You seemed a little too happy.
Well, I'm just saying, I mean, things don't always work out the way you want them to work out. They just work out the way they are. I'm not, trust me, I'm not happy. But it has to happen. All right, so I need to draw that thing. Well, remember, it's just the outer shell, right? So if I look at it from this perspective, this is the YZ, right? It's just the outer ring of this, which is just a circle of radius 1 in the YZ plane, which I can draw pretty easily by letting my Y and Z components be cosine, let's say U and sine U. That will draw me circles of radius 1 in the YZ plane, right? That's what we'll draw. The outer edge. It's not going to draw me the disk, just the outer edge. Remember, the green is just the outer edge, right? So I want to be able to draw that. But at the same time, while I'm drawing that, I need to be drawing the back and forth, the green part. That's the x, right? So for the x, I'm going to call this v. And then I'm going to control it down here in the restrictions with the domain. So my u will go between 0 and 2 pi. That will help me draw that circle. And then my v is always stuck between, so this is, your v is actually your x, right? So you go back and forth between here and here, which is always, what's that backside? 0, and the front side is that right there, right? 1 minus z, but what's z for us? Sine u. Okay? So this is going to go from 0, which is the red plane on the back of the surface, solid, whatever, up to the front side, which is 1 minus z, but I'm not using z because I've changed everything over. That's sine u. There it is. Yes?
Quick question. If we were to make it so that that was solids of v cosine u, you know, like we've had, what would the meaning of that be? Because then we would have a solid.
Wait, what if we made what?
So it was v comma v cosine u, then v sine u, so we had a solid shell instead of it just being the shell.
It's never going to draw you a solid.
Okay.
It's never going to draw, two variables, never going to draw you a solid.
Okay.
It's always going to be a surface. So you're asking a question that's taking us off on a tangent.
Right.
Yeah, okay. All right, good? What do I do now? Cry, yes. So can we evaluate this function, scalar function, on that? Can I? Yes, right? What am I going to plug in for x? V. But then I need the magnitude of the cross product of the partials, don't I? I haven't done that yet. So partial of r with respect to u is, okay, with respect to u, I get derivative that's 0. This is negative sine u. This one is cosine u. That's partial of r with respect to u. Now I need partial of r with respect to v. 1, 0, 0. Ooh, that's nice, right? Cross this. If I cross, let's see, lots of things are going to be gone. 0, 0. Wait, is that right? Hold on.
Yeah.
Wait, I did that one. This one right here, I get 0, and then I subtract cosine. Cosine u. The last one, no, because, well, yeah, it'll turn out positive because you do this times this, 0, and then you subtract this times this, but then you have to put the negative in front. And it's not going to matter because we're going to take the magnitude, so we're going to square it anyway. So it's not going to matter, but we want to get it right, right? So there, 0, and then here to here, minus minus plus sine u. Ooh, happy about this. Happy about this, right? Because the magnitude of that is 1. Right? Square it, square it, square it, add them together, Pythagorean, you get 1. All right, I'm ready to set it up now. I'm going to do the double integral over d. D is this, right? D is this. Can't see d, right? I can't see it. It's not on my picture. D is in the background somewhere. And now the actual function, the scalar function f, which we said was v, times the magnitude of the cross product of the partials, which was 1, and then dA. Now I can put my limits of integration. So do I get to choose the order? I do not, because one of them depends on the variable u. So I'm going to go outer one is 0 to 2 pi. Inner one is 0 to 1 minus sine u. And I'm integrating v dv du. Can you integrate v? Okay, and then could you plug that in? It's actually not a very pretty integral because you'll get like sine squared in there. and it would require like power reducing, and it's a little tedious, but within the capabilities of a Cal 3 student for sure. In theory.
You might be over.
In theory. So I'm again going to cheat here. I'm going to go, what do we got? 0 to 2 pi, 0 to 1 minus sine u. I can use u and v here. And then in here is just v, maybe, in the glasses. Can you all even see that? Yeah, okay. And then, yeah. Okay, so d v d u. Three pi over 2. 3 pi over 2. Let me double check that. Did I do this one? Pardon me? Yeah, now we add up all those answers, and that's our answer. So our final answer is root 2 pi plus 3 pi over 2. That is the surface integral of this scalar function f over that surface S, which is the union of all three surfaces. Are we having fun yet? Oh, yeah, I did do that one. Okay, that verifies. You're not having fun yet? Okay. Then we need to do more. We're going to keep going until you have fun. It might never happen, though.